Hi everyone, so you are welcome in my lecture series on digital signal processing. In my last video, we discussed about linearity property of Z transform, and we have seen that if x1 z transform is x1 and z transform is x1z with ROC R1, x2n's z transform is x2z with ROC R2, then what would be the z transform of the linear combination of x1 and x2? So this a1 times x1n plus a2 times x2n, this is a linear combination of x1 and x2, and the Z transform of this linear combination would be the same linear combination of x1z and x2z. That is, the Z transform would be a1 times x1z plus a2 times x2z. And what about the ROC? ROC would be at least R1 intersection R2. So I can say the ROC R will contain the common region between R1 and R2, and it means that this ROC could be greater than the common region between R1 and R2. We saw that if we combine two infinite duration sequences, let's say un and un minus 1, and if we make a new sequence which is un minus 1, then we get delta n, which is a finite duration sequence. And this finite duration sequence ROC is more than the ROCs of UN and UN minus 1. In fact, UN and UN minus 1's Z transforms are having ROC mod Z greater than 1, whereas the Z transform of delta N is 1 and its ROC is entire Z plane. So this confirms the fact that ROC of the linear combination may be sometimes greater than the common region, and in fact I explained when it would be more when there is some pole zero cancellation. In that case, the ROC of the linear combination would be more than the intersection of their individual ROCs. So now can we make this linearity property more general in the sense, instead of taking only two sequences, can we have n number of sequences, let's say x1 x2 x3 and so on, and if we take the linear combination of these n sequences, that is, if we have a1 x1n plus a2 x2n plus a3 x3n and so on, so this is the linear combination of n sequences. What would be the Z transform of this linear combination of n sequences? It would be the linear combination of the Z transform of these sequences, that is a1 x1z plus a2 x2z plus a3 x3z and so on. And what about the ROC? Again, the ROC will contain R1 intersection R2 intersection R3 and so on. So again, the ROC is a superset of intersection of the region R1 intersection R2 intersection R3 and so on. So this is a general version of linearity property. Now we will solve some examples on linearity property. So let's say we have a sequence xn equals 2 times half to the power nun plus 4 times 3 to the power n u of minus n minus 1. In fact, we have done this kind of problem before, but that time we solved problem without using the linearity property. Now we shall make use of linearity property. So here this sequence is like x1n, this 2 is our a1. Similarly, so this a1 is 2, this 4 is a2, and this sequence 3 to the power n u of minus n minus 1. This is our x2n. So what is Z transform of x1n? x1n Z transform would be 1 upon 1 minus half Z inverse with mod Z greater than half. And what would be the ROC? What would be the Z transform of this x2n? So x2n Z transform would be 1 upon 1 minus 3Z inverse with mod Z greater than less than 3. So these are our x1 and x2. So now we have to find Z transform of linear combination of x1 and x2. That is, we have to find Z transform of a1 times x1n plus a2 times x2n. So from linearity property, can we write the Z transform directly? So what is our a1? Our a1 is 2. What is our x1z? It is 1 upon 1 minus half z inverse. Then what is the Z transform of x to n? There is a correction. This is not 1 upon 1 minus 3z inverse, but there would be a negative sign as well. So put this minus sign here. So this is minus sign. So what would be the Z transform of this linear combination? 2 times 1 upon 1 minus half Z inverse minus, now what is our A2? 4. So 4 upon 1 minus 3 Z inverse. Now what would be the ROC? The ROC would be at, what would be the ROC? ROC would be at least the region which is common to both. Common to both means mod z greater than half and mod z less than 3. So what is the common region? So common region would be a ring between the circles of radii half and 3. So here the ROC would be mod z lying between half and 3. So this is the Z transform of the sequence a1 x1n plus a2 x2n. So we have obtained the Z transform of this sequence, and if you simplify these expressions, then you will see that there won't be any common factor between numerator and denominator. There won't be any pole zero cancellation, and therefore the ROC is exactly R1 intersection R2. Now, if there had been some pole zero cancellation, the ROC would have been more than R1 intersection R2. Now, we take another example. What would be the Z transform of this sequence? E to the power j omega naught n u n, where omega naught is some real number. It could be 0.32, any real number. What is the Z transform of this? Now, without using any property, if you remember that we have already done Z transform, we have already obtained the Z transform of this sequence, where alpha is a complex number. It could be complex, it could be real. So in general, alpha is complex. Then the Z transform of this sequence we obtained, it was 1 upon 1 minus alpha z inverse with mod z greater than not alpha but mod alpha. Similarly, we saw the Z transform of minus alpha to the power n u of minus n minus 1, its Z transform was 1 upon 1 minus alpha z inverse with mod z less than mod alpha, that we have done before. So now if we use this expression and we try to find out the Z transform of this sequence e to the power j omega naught n u n. So what is our alpha here for this sequence? If we compare, so what is alpha? Alpha is nothing but e to the power j omega naught. So if we write the Z transforms expression for this sequence, what we can write? It is 1 upon 1 minus alpha. Alpha is e to the power j omega naught z inverse with ROC mod z greater than mod alpha. So what would be the mod of alpha? So mod of e to the power j omega naught, it would be what? 1. So I can write it is greater than 1. So we have obtained z transform of e to the power j omega naught n u n. It is 1 upon 1 minus e to the power j omega naught z inverse with mod z greater than 1. Now, instead of this, if I ask what is the z transform of e to the power minus j omega naught nun? So the problem is same. Here, what is our alpha this time? If you compare, the alpha is e to the power minus j omega naught, and there is no other change. So what would be the z transform of this sequence? Again, 1 upon 1 minus alpha. What is alpha this time? E to the power minus j omega naught. So I have written alpha as e to the power minus j omega naught multiplied by z inverse. And what would be the ROC? Mod z greater than mod alpha. So what would be mod of e to the power minus j omega naught? Again it is 1. So it is greater than 1. So these are the z transform of these two sequences. Now using these z transform and using the linearity property of the z transform, can we find the z transform of some other important sequences? So let us take this sequence. Xn equals cos omega naught n un. We want to find out the transform of this sequence using linearity property. So before using the linearity property, can we write cos omega naught n un in terms of complex sinusoids, that is e to the power j omega naught n and e to the power minus j omega naught n. So from Euler's identity, we know what we know. We know e to the power j theta is what? It is cos theta plus j times sine theta. And you know cos theta can be written as e to the power j theta plus e to the power minus j theta by 2. So instead of writing by 2, I am writing like this. So can I express cos omega naught n in terms of complex sinusoid? E to the power j omega naught n and e to the power minus j omega naught n using the Euler's identity. So using Euler's identity, I can write it is e to the power j omega naught n un plus e to the power minus j omega naught n un divided by half. So instead of writing dividing by half, I am multiplying both the components by half. So now our sequence is this. So can we find the transform of this sequence using linearity property? Again, if we compare this sequence with the sequence a1 x1 n plus a2 x2 n. So what is our a1 and what is our a2? So this half is like our a1. This e to the power j omega naught n un, it is like our x1 n. This half is like a2 and e to the power minus j omega naught n un is like x2n. So z transform of this sequence can be obtained using linearity property. So what is our a1? Our a1 is half. Now we have already obtained z transform of x1, that is e to the power j omega naught n un, and it was what? It was 1 upon 1 minus e to the power j omega naught z inverse plus a2. a2 is half into x2z. What would be the x2z? Z transform of x2n. We have already computed it and it is 1 minus e to the power minus j omega naught z inverse. Now what about the ROCs? The ROC of this component is mod z greater than 1. ROC of this component is also mod z greater than 1. So what would be the common region? Common region would be R1 intersection R2. What it would be? It would be mod Z greater than 1. And we will see whether there is any pole 0 cancellation. If there is some pole 0 cancellation, ROC would be greater than R1 intersect. Greater than means larger than R1 intersection R2. Otherwise, it would be exactly same as that of R1 intersection R2. So now we simplify this expression. So on simplifying, what we'll get, so xz I can write it is 1 upon 1 minus half e to the power j omega naught z inverse, and I have taken this half outside, plus 1 upon 1 minus half e to the power minus j omega naught z inverse, and I am writing here what is R1 intersection R2. It is R1 intersection R2 is what? Mod z greater than 1. Now we simplify this, so we take the LCM. On taking LCM, we get 1 minus half e to the power j omega naught z inverse multiplied by 1 minus half e to the power minus j omega naught z inverse, and half is outside, so I write this factor 2 here. Then I get 1 minus half e to the power minus j omega naught z inverse, then plus 1 minus half e to the power j omega naught z inverse. Now, if I simplify the numerator, if I combine the terms of z inverse, so what I get? First 1 plus 1 we get 2, then we get minus z inverse, and then we have e to the power minus j omega naught plus e to the power plus j omega naught. And if we simplify the denominator, what I get there is this 2 factor, and here we get what? 1 multiplied by 1 will be 1, then minus half e to the power minus j omega naught z inverse, then minus half e to the power plus j omega naught z inverse, and when you multiply these two factors, so you get what? You get, okay, so this half factor is not here. I'm sorry for this half factor. So let me remove this half factor. This half factor is not here. This half is also not here. This half is not here. This half is not here. This half has to be removed. Then here it is okay, and then half has to be removed here. I'm sorry for this correction, but okay, so now we are done. So this is the expression. So now if we simplify this, we get 1 minus e to the power minus j omega naught z inverse plus 1 minus e to the power j omega naught z inverse, and the denominator, again this half has to be removed from here. This half has been removed. So now I combine this term. So what I get? E to the power, in the denominator we will be having this, when we multiply we get plus z to the power minus 2. And if we further simplify this expression, what we get? We get xz equals what? Is equal to. Now, here again you can combine the terms in numerator. Which terms you can combine? Here you can write this as what? 2 cos omega naught. So I write it 2 minus z inverse 2 times cos omega naught. In the denominator, again these two terms can be combined. So you get 2 times 1 minus. So when you combine these two terms, you get minus 2z inverse cos omega naught n plus z to the power minus 2. And if we further simplify, if we take 2 common from the numerator as well, we get 1 minus z inverse cos omega naught upon 1 minus 2z inverse cos omega naught plus z to the power minus 2. And now we can see there is no cancellation between numerator and denominator's factor, and therefore the ROC R will be R1 intersection R2. And what was the R1 intersection R2? It was mod Z greater than 1. So we have obtained Z transform of the sequence cos omega naught NUN. On the same lines, can we obtain the Z transform of the sequence xn equals sine omega naught NUN? So again, we make use of Euler's identity, and xn can be written as half e to the power j omega naught n un. Not half, this time there should be 2j minus 1 upon 2j e to the power minus j omega naught n un. Now this time what is our a1 x and x1? So our this 1 upon 2j is a1. This e to the power j omega naught un is our x1n. And this time what is our x2? Our x2 is minus 1 by 2j. So this is our a2. Sorry, it's not x2, it is our a2. And what about x2? So x2 is this sequence. So can we write the Z transform of the sequence a1x1n plus a2x2n using the linearity property? So it would be a1 is what? 2j, and Z transform of e to the power j omega naught n un, it is known to us. I can write it is 1 upon 1 minus e to the power j omega naught z inverse minus 1 upon 2j. What is the Z transform of x2n? It is 1 upon 1 minus e to the power j omega naught z inverse. And what are the ROCs of x1z and x2z? Again, the ROC of this is mod z greater than 1. ROC of this component is also mod z greater than 1. So R1 intersection R2, it is what? Mod z greater than 1. And we will see that if there is no whole zero cancellation, then ROC would be exactly same as that of R1 intersection R2. And if there is any whole zero cancellation, then it may be larger than that. Now we simplify this expression. So this expression on right hand side I call xz. Again, if you take the LCM would be the same as that of previous 1 minus e to the power minus j omega naught z inverse multiplied by 1 minus e to the power plus j omega naught z inverse, and then there is 2j factor outside. And in the new, if you solve this, in the denominator, uh, you have this. Now in numerator, what you would be having? You would be having 1 minus e to the power minus j omega naught z inverse. Then there is a minus sign. So minus 1 and then plus e to the power j omega naught z inverse. So if we simplify the expression, you can see this 1 cancels by minus 1, and then you can collect the terms of z inverse. So z inverse terms, when they are collected in the numerator, you get what you get? You get 2j sine omega naught z inverse. This is the numerator. And what about the denominator? Denominator is 2z 2g 2j multiplied by 1 minus 2z inverse cos omega naught plus z to the power minus 2. The numerator expression is almost similar as that of our previous case. Now this 2j cancels with each other. So we have sine omega naught multiplied by z inverse. So I write z inverse here, divided by 1 minus 2z inverse cos omega naught plus z to the power minus 2. And again we see that numerator and denominators are relatively co-prime, and therefore the ROC would be R1 intersection R2, and R1 intersection R2 has been obtained. It is mod Z greater than 1. So we have obtained the Z transform of two important sequences, namely cos omega naught n un and sin omega naught n un. Thus, we see that this linearity property is very useful. If we remember the Z transform of some standard sequences, then it is possible for us to find Z transform of some new complex sequences. So, with this, I stop here. Thank you very much for watching my videos.